was actually a pretty pleasant experience.
Oh, wow.
I haven't done that in a while.
Hey, this is Warren Redlick. One of the great things about Elon Musk is not just that he is brilliant, but he puts together brilliant people on a team. One of the people who stands out the most in Elon's team building is Andrej Karpathy. Andrej Karpathy is essentially the head of Tesla's full self-driving effort. The ability to get the cars to drive themselves, to use machine learning, neural networks, and all of that. And Andrej Karpathy just had a great interview on a podcast called Robot Brains, a brand new podcast. We're going to break that down today. Are you ready? Let's go. Full self-driving is the feature on Tesla vehicles that allows the cars to drive themselves. As you can see here, the car is driving itself without any hands on the wheel. Currently, when people are driving FSD, they're supposed to have their hands on the wheel ready to intervene, and that is what is normally done. This was a demonstration, but this is where we're heading, to where the car will drive itself and you won't have to touch the steering wheel, or where there won't even be a steering wheel. It looks like magic to a lot of people. It's coming fast, and Karpathy gave a great explanation of some of the steps in this interview we're going to go through next. Before we go further, I want to thank the Vasa Law Firm in Sweden and all my Patreon supporters for helping this channel grow. Please check the description below for a link to Patreon to help out this channel. And as always, we have great t-shirts. Elon Be Less Wrong is the most popular t-shirt on the website. Elon Be Less Wrong. Link below to elonbits.com. And of course, I wrote a book, Fair DUI. If you like how I talk about things, you might like this book to learn how to handle yourself if you get pulled over by the police, whether you're sober or not. So let's get into that interview.
Actually, Elon reached out and he asked me, hey, you've been like sort of consulting for the team. Do you actually want to join and lead the computer vision team and the AI team here and help get this car to drive? And so he caught me at a very kind of correct time when I was really getting restless, and I felt like this is perfect. And I think I can do this. I think I have the skills to contribute here. This is an incredibly impactful opportunity. And I love the company. And of course, I love Elon and everything that he's doing. And so I would say that, again, sort of it was a moment where stars aligned for me. And I felt very strongly that this is the right thing to do at this time. And so I left OpenAI, and I've been at Tesla for the last 4 years or so almost.
I'm going to go over excerpts from that interview. I encourage people to go to the Robot Brains podcast and listen to the whole thing if you really want to get all the detail. There's a lot of background on Karpathy and how he got to Tesla. This was just the very, very last bit of it, that he worked at OpenAI, which was an Elon Musk project, and Elon brought him into Tesla, where he felt he could have great impact. That delivering full self-driving cars is a massive impact on making the world a better place. And that's what he wants to do. And it's also a great place to implement all the things he's learned and all the things he's been teaching about how to make artificial intelligence, machine learning, and neural networks work to improve life, make things better for humanity. Now, here's a quick bit about what it's like to work for Elon.
This is a job that on average people last 6 months. And here you are, almost 4 years, and knock on wood, this is just amazing.
Yeah, that's accurate. I was aware of the average tenure at Tesla, especially when you're working on very important projects very close to Elon. And so, yeah, I was very much aware of this. So when I made the transition to Tesla, for example, I did not give up my apartment in San Francisco because I was just kind of like, really hedging my bets on what's going to happen in the next few months. But yeah, here I am 4 years later, still here.
One of the things that struck me in the interview is this part coming up. You see a lot of people in the media, a lot of political figures like Bernie Sanders and Robert Reich, Business Insider, attacking Elon's character as if Elon is this evil monster. And it's really interesting to hear from Andrej Karpathy, who has worked closely with Elon for 4 years, to see how he sees Elon, which I would say, when you hear this, you're going to agree with me. This is a much kinder description of Elon and his motivations than the attacks you hear from others.
Well, he's obviously a very incredible person in many ways. I'm still trying to really map out his superpowers. He has incredibly well-developed intuition, I would say, in many aspects, where he makes the right judgment calls, sometimes in what I perceive to be a lack of information, because he's not fully in detail of all the things, but yet his judgment is extremely good. I still haven't fully understood how that happens. He has a way of taking a very complex system and simplifying it to just like the fundamentals and the first principle components of what really matters about the system, and then making statements about those. And so it's a very different way of thinking that I find kind of fascinating. By default, for example, sometimes I get sort of overwhelmed by the system. I feel like I need to know the system in its full detail to make the correct decisions. But that's not how he operates. He somehow has a way to distill the system into a much simpler system in which he operates. And so I think I've learned a lot about just how to approach problems. He's a double-edged sword because in terms of working with him, right? Because he wants the future yesterday. And he will push people and he will inject a lot of energy and he wants it to happen quickly. And you have to be of a certain, I think, attitude to really tolerate that over long periods of time. But he surrounds himself with people who get energy out of that. And they also want the future to happen quicker. Those people really thrive at Tesla. And so I happen to also, I think, be like that. And so I don't personally mind it. I actually kind of thrive on it. And I love the energy of getting this to work faster, making a difference and having this impact. And so I really enjoy working with him because he has a way of injecting energy into the system, driving momentum, and he has incredibly good and developed judgment. But yeah, I overall just really, really enjoyed working with him. Elon sort of has a number of companies and a number of bets around just a higher level goal of making the future good, increase the probability of the future being good.
A high level goal of making the future good. Yeah, that sounds like something I'm going to like. How Robert Reich and Bernie Sanders and all these haters at Business Insider, all these other places attack him, Tesla Q, they keep attacking Elon, when the people closest to him know that his goal is to make the future good. But before we get deeper into full self-driving, listen to Andrej Karpathy explain why full self-driving is a part of making Tesla vehicles better and why this matters to you and to humanity.
There's many aspects to that, of course, and he's focused the Tesla mission around accelerating the transition to sustainable energy. Fundamentally, a large piece of this is getting people to transition to electric vehicles, and we need to manufacture them at scale, and we want them to look like the future. And so the entire product itself sort of looks like the future. It's a very clean design, and you want to be inspired by progress in society and that things are developing in a positive direction. It just becomes something magical in your life that can take you around in this beautiful future. And so I think autonomy really is just a broader vision to this future that we want to be part of, where we are driving electric vehicles with very little footprint and the society is sort of automated to a large extent. And there's a huge amount of problems, of course, also around transportation and putting people in the loop with the amount of accidents that they get into. And also with the fact that you don't want people to be really driving these cars because human brain is capable of so many beautiful things. So why should you solve the line following problem? That is not a good use of the brain. So not only is it unsafe to drive these cars, it's also just you want the brains to be doing something different.
So now listen to Andrej Karpathy get into some of the specifics about why it's hard to make self-driving work.
You have to deal with a huge amount of variability of what the world looks like. It's basically true that for AI and technology as it is today, the degree of difficulty is proportional to the degree of variability you're going to encounter in the application. So the more scenarios you have to deal with, the harder it will be for the technology. And that's what makes this hard for self-driving cars as well, is that environments out there are quite variable. Maybe on the highway, you're just dealing with lane following, but once you get off the highway into city streets in San Francisco and so on, the amount of things you can encounter is very large. And designing to it is incredibly difficult.
Next, Andrej explains a little bit of the basics of neural networks. You might have to listen to this bit a couple times to get it. I'm still not sure I get it, but listen, see if you get it.
These neural networks, they are made up of neurons like your brain. It's not an exactly correct analogy and it's misleading. It's better to think of them as a mathematical function with a lot of free parameters, 60 million knobs that must be set to get the correct behavior. And in the beginning, the setting of these knobs is completely random. So the neural net is implementing a completely random function. It's doing completely random things. And it's starting basically from scratch. And you have to tell it what to do in every situation. And the more situations you have, the more you're going to have to give it in order for it to do the right thing in all the cases. So if I want the neural network to function in millions of situations, I need to plug in millions of examples. and or something on that order. So the neural networks do show some ability to sort of interpolate between the examples you've given them. They're not as good at extrapolating, but as long as you sort of cover the space of possibility and tell the neural network what to do in those different scenarios, they have some ability to interpolate between examples, but it's limited. And so if you really have a massive amount of variability that you want the system to perform well on, you actually have to cover that space to a large extent.
All right, so I'm going to take a stab at this. You have a network of neurons, and they have a bunch of weights, and a bunch of data comes in, and the data goes through these layers of neurons, and the weights that have been determined by the training that happened before. We're going to talk about how training sets the weights a little bit later. The information goes through, and the software interprets based on what information it's seen, how it's supposed to assign things, what its output is supposed to be. And there's a really important detail in there that Andrej mentioned about being able to interpolate. It's not going to see every one of an infinite array of scenarios. You're going to show it millions of scenarios, but there are an infinite array of things that can happen. But if the two scenarios are close enough to each other, if the scenario that occurs is close enough to two other scenarios that is seen, if they're close enough and it's not that much different, it's able to interpolate. It's able to figure out, okay, I'm between this one and this one. Or if there's 4 around and it's in the middle of a group of them, it's able to say, okay, I'm kind of close to these, I can kind of wing it. But it's fairly limited in going beyond that. That's how I got it. Now let's get in a little bit into how the machine learning works, how the neural network learns.
Fundamentally, you roughly start with some data set and you train your neural network. Then you measure its performance and you look at where it works and where it does not work. Fundamentally, the way you're iterating on this neural network to get it to work is you need to find a lot of examples where it does not do what you want it to do. And then you need to get those situations and you need to label correctly what should have happened in those situations, what the correct label would have been in all those cases. And then you need to put those into the training set for the neural network. And so the neural network is now trained on the previous data set, also on a data set of where it failed before, but now has the correct label. And this improves some situations again. And then you have to again look at where it's failing now. The faster you can spin this loop of just iterating and curating your data set, the better this neural network will become. And luckily, we are in a position with these deep neural networks that as long as the data set is improving, there's no real upper bound on the performance of the network. If you have enough computation available for it and a large enough data set, it will find the correct sort of solution, making your labels work. So most of the engineering is on the data set. And primarily, it comes from sourcing examples where you're not working yet.
And sourcing examples where it's not working yet, is that when I drive my Tesla, am I sourcing those examples? How does that work?
Yeah, exactly. So it's a great question. A lot of what I do, of course, at work is just curating these data sets, as I mentioned. That's where all the engineering now is. It's not people writing algorithms, it's people collecting data sets. There's lots of things we want to know about the scene, right? So we want to know where the lines are, where the edges are, where the traffic lights are, where the other cars are, whether or not the car door is open on the car, if the left blinker is on, a huge amount of things. So roughly we have maybe say 30 top level tasks, but a lot of those tasks have many subtasks. Like for a car, you may want to know a lot of attributes about it. What kind of a vehicle is it? Is the car door open and so on? So you end up with a huge amount of predictions that your neural network has to make about the world. And now these networks are deployed in people's cars and they're running and making predictions. And then we have to come up with lots of ways to source inaccuracies. There's many ways by which we do that. Maybe one very simple example is if you intervene because the autopilot did not do something correct. Typically, when you intervene in a large number of cases, that has to do with an incorrect prediction from the network. So an intervention is a trigger, and we collect some of those images, and then we look at them, and we look at whether or not the predictions were correct and how were they wrong. And that helps us triage, should this example go into what labeling project, and where should it end up in what data set and with what label. And that's how we sort of iterate on the system. But there's many triggers that are active at any point in time. As one more example, if you have a detection of, say, a stop sign or something like that. So you have a bounding box that the computer is putting around the stop sign. And if the stop sign detection flickers, for example, so it's there and then the network says, oh, it's not a stop sign. Oh, wait, it is a stop sign. When you see this disagreement with itself over time, that also is typically an extremely good source of data. So flicker and temporally inconsistent predictions, or for example, disagreements with the map. So we think there's a stop sign, but the map says that there isn't one. So there's lots of different ways by which we gather examples where the network is mispredicting. And for us, it's an exercise of how quickly can you enter those examples into a training set.
This is something I've been talking about for a while. When most people talk about full self-driving, Tesla's full self-driving, there's this notion that the full self-driving software learns when a human intervenes, when the car is driving and the human grabs the wheel and steers in a different direction than the car was trying to go. When a human hits the brake, when a human hits the gas, when there's some intervention, that is something that gets relayed back to the home office and they try to figure out, okay, what happened here and how do we train the software to do better in that situation? Which is good. That's something that's really important that FSD has been learning from so far. The problem is that humans aren't perfect. Humans make mistakes, and humans, on the one hand, a human correction might be wrong, and on the other hand, a human might not correct when there's something to be learned from. There might not be an intervention where there was something the software could learn from. So there's other triggers, is the word that he used, other triggers that FSD uses to learn from. And I've been talking about, kind of wondering, well, what is it learning from? And I'm pleased to say I kind of nailed one. One of the things I said was, well, the software is following along, even when the human is driving in what's called shadow mode. It is watching the road. What the software is doing is there's a couple of steps. First of all, it sees objects and identifies, this is a stop sign, this is a car, this is a pedestrian, this is a dog, this is a tree. It's making these identifications of objects. And there's two things it's doing with these objects. Now, there may be more than two, but there's two that I'm aware of. One, it's identifying what is this object. And two, it's predicting where is this thing going to move. So what Karpathy just talked about was, if the identification is flickering, this is a stop sign. Wait, it isn't a stop sign. This is a stop sign. No, it's not. Or if the identification conflicts with some other data they have from mapping. Their map says there's a stop sign here, but the software is not identifying that as a stop sign. These are triggers that get sent back to the home office so they can retrain the software so that it will do better in the future. There's a second thing that he didn't talk about here. It's also predicting paths. So if it sees a stop sign, it's going to predict the stop sign's not going to move because stop signs don't move. Trees don't move, stop signs don't move. Cars move, pedestrians move, dogs move. So it's going to form some kind of prediction. If you go back and watch the Jim Keller interview with Lex Friedman, Jim Keller is a chip designer who worked on the FSD chip that Tesla is using now. Keller talked about what the software is doing is it's identifying objects and it's assigning ballistic probabilities to them, where they're likely to move to. And so if the software predicts that something's going to move from here to there, and it moves from here to here instead, or it has a range of where the thing's going to move to, and it moves outside that range, that is a trigger to look at to say, wait a minute, we predicted something wrong here. Let's learn from this. This is a really important step in how FSD is going to get better, because once it gets better than human, it really can't learn that much from humans anymore in terms of our interventions. At that point, it needs to learn from other things. So identification of objects, it should be able to tell, did I identify that correctly? Prediction of where things are going to go, it should be able to tell, did I predict correctly or not? And these are steps, and there's other things. We just heard that they're using LiDAR on some vehicles for training. Not going to go on the regular Tesla cars, but they put LiDAR on a car that's in training, and the LiDAR is able to determine the distance to various objects. If that distance doesn't match up with what the software says it thinks the distance is, that's another thing to learn from. So the goal is to give the software as much data as possible so that it can check itself against the real world, or best estimates of what the real world is, ground truth, and it can improve its predictions. It can improve its identifications, it can improve its predictions, and ultimately it can improve the probability, or minimize the probability of hitting something, which is the goal, right? You want to be able to get where you're going, and you want to not hit anything. That's what we're trying to do. Next up, Andrej Karpathy talks about training compute time. There's two different things going on. You're going to hear this again and again. There's the chip in the car that is processing the training. It gets the input, it runs it through, and it puts the output. There's a second part of AI machine learning, which is the learning part, where all the data and all the experience and everything else is sent back to the home office, and there's computers at the home office, some kind of cluster, eventually dojo, that processes all this information and goes through the process of setting the weights in the inference computer. The inference computer's in the car, training computer decides, okay, based on everything we've seen, let's back propagate, let's go back through and see if we can come up with a better set of weights so the car learns better, the car performs better under all the circumstances it's seen so far, and interpolating the ones in between.
How much compute does it take? How long does it take to train an autopilot?
What you're getting at is these neural networks are quite expensive to train. So we start with millions of images. And typically what you will see in the industry is most networks train roughly on the order of 2 to 3 weeks. Because 2 to 3 weeks is actually more of a psychological reason for that, is because that's the amount of time that a person is willing to wait for the network to converge and to measure its performance. But yeah, they have to look at a lot of examples. They have to make a lot of predictions, and they have to be corrected on the predictions they're making during the training loop. And this takes a long time. And as you are scaling up the amount of compute available, you can afford to use a bigger network. And a bigger network will almost always work better, but it needs more training time. And so we're in a place where we are, and this is a beautiful place to be, by the way, we are not constrained by human ingenuity and algorithms, as used to be the case in computer vision, because we had a class of approaches that leveled off, and then we were the constraint. But now, human ingenuity is not a constraint. The constraint is the size of the data set and the amount of compute that you have available to you. The algorithm now is known, everyone knows the same algorithms, and we just need to run them at scale. And we're getting benefits for free just by scaling up the network, making a bigger network, and making a bigger data set. So it's a beautiful place to be because you have a recipe, a template by which you can make progress, and you're just bounded by very concrete, tangible things that you can improve, like the size of your training cluster and things like that.
Thing is, I'm not James Doma. I'm not Andrej Karpathy. I'm going to do my best to explain what I think Andrej is saying here, is that you've got all these neurons. The more neurons you have, the more data you can throw at them, the more time you have to give them to adjust to the errors that are found, the more effective your software will learn. And there's a couple things going on here. There's compute, the amount of computer resources they have. And if you can throw more computer resources in, you can increase the number of neurons. If you can get more data, one of the beautiful things about Tesla is they're building this huge network of cars that are all collecting data, so they have more data. So you can throw more images, you can throw more ground truth at the network, and you can run that through with more computing resources. And I think more is coming with Dojo. We'll talk about that a little later. You put all that together and your software improves. Now, there's this window of time that it takes to train that Karpathy said it typically takes 2 to 3 weeks, and it's not really a technical barrier. It's just sort of psychologically. That's how long humans are willing to wait for their software thing to train before they run it again. And I think one of the things that Tesla is working on is getting that training time down to a week and then shorter. So these are the things that are happening that are working to make full self-driving happen and to make machine learning happen faster, to make neural networks improve faster and get us to a better place. Next up, Andrej was asked about the amount of time they spend on algorithms versus the amount of time they spend on other things like curating data. And the questioner's impression was that they don't have to worry about algorithms anymore. Andrej has said the algorithms are basically settled, but it's not completely true. They're still working on making their algorithms better. The algorithms are figuring out how to make the software learn better. The software side of how do we set this up so it learns better? How do we program the training so that it learns better? What kind of approaches can we use to make that work better? As opposed to throwing more neurons in, throwing more data in, getting better data. And the way he talks sometimes, it sounds like, well, the algorithms are already settled. He just said that in the previous segment. But the algorithms are not completely settled. There's still room to be gained. And you're going to hear him say, we spend some time on algorithms still. There's other fields of AI and machine learning where a lot more time needs to be spent on algorithms. And I think a part I left out of this interview, he talked about in academia, when you're in an academic setting in a university, they spend a lot more time on algorithms. In the industry, in the real world, they don't spend as much time on algorithms anymore because there's not that much to gain by adjusting algorithms. It's really about getting data, getting compute power.
It's a good observation that the algorithms, it's not fair to say that they're fully figured out and known. I would say it's more true in some domains than others. Like in computer vision, I think we have a class of algorithms that we're pretty happy with for the simplest image recognition problems. in many cases, for example, you're dealing with robots doing pick and place and things like that. I would say algorithms are totally much less known. So different domains will have different maturity of the technology available. I also want to say that it's not the case that we spend zero time on algorithms. It's more like we spend 25% of the time, not 100% of the time.
Next, Karpathy gets into this really big topic of basically software 2.0, which is neural network programming, machine learning, eating software 1.0. The good old days, humans wrote code that told the computers what to do, took the input, set the output. It was all driven by humans deciding, when you have this input, do this output. And neural network programming, neural networks are much better at learning from very, very complex inputs. We humans can't anticipate every input and then tell the computer what to do with every different situation because the world is just too complex. And the beauty of neural network computing is with enough neurons, with enough compute time, with enough training, it can learn to handle situations we could not possibly code for. So listen to what Andrej has to say about that.
A lot of the software right now is written by people. So, banking systems and, internet search and things like that. Everything is sort of algorithms developed by people, in principle understood and orchestrated in a certain way. It seems to me basically that with progress in deep learning, you can sort of think of that neural network as a piece of software, but the software was not written by a person. The software was written by an optimization. And so it's kind of like a new programming paradigm that we are not directly writing the algorithm. We are programming the data sets, and the algorithm really is an outcome of this training process or this compilation, which would be sort of the equivalent in typical software. So you would take your source code and you would compile it and get a binary. So here the source code are the data sets. The compilation is the training of the neural network, and your binary is the final neural net, the weights. And to me, what's happening in society right now is that we are, well, number one, a lot of software that we couldn't have written before is now possible to write, like image recognition systems. But also, a lot of software that used to be written by instruction, software 1.0 style, can now be ported over to this more powerful paradigm, to software 2.0. And the programming sort of looks different.
Coming up, Andrej does his own breakdown of the difference between the chip that's in the car, the computing resource that's in the car for machine learning, that's applying the learning, and the computing resource that's used to train those inference computers. Inference computers in the car, training computers are in basically the home office, some base where the training takes place. Hear what he has to say.
In the car, there are both. Images enter in the beginning, right? And we have pixels of an image telling us fundamentally what's out there in the world. And then neural networks are doing some portion of the recognition. So they're telling you, hey, there's a stop sign, person, etc. But you can't just directly drive on person, stop sign, etc. You have to actually write some logic around how do you take those intermediate sort of representations and predictions, and you want to avoid the pedestrian and you want to stop at the stop sign. And so there's still a lot of software 1.0 code sitting on top of the neural net. And that code is basically reacting to the predictions so that it speeds up, slows down, turns the wheel to stay in the lane line markings and so on. What I have seen in the history of the team since I joined 4 years ago, we've been porting a lot of the functionality from the software 1.0 land into the neural network. And so originally, the neural networks would only make predictions, for example, for a single image, and they would tell you, okay, there's a piece of a road edge. But we actually don't just have a single image, we have 8 images, right? Coming from 8 different cameras that are surround in the vehicle. So every image independently predicts little pieces of road edges and curves, but there needs to be something above it that stitches it up into a 3-dimensional sort of bird's eye view of what's happening around the vehicle. And that was all done in software developed by people. So you take road edges from here, you project them out, road edges from all the cameras, project them out, stitch them up across boundaries. And then over time, you need to also stitch them up and track them and make it sort of temporally continuous. And all that was written by people. And what we've done since then is the neural network has engulfed a lot of the pieces of the engineering. So the neural networks that are in the car today will not make a prediction per image. They will make prediction directly in the bird's eye view. So they will say, okay, I've seen these 8 images, and from that, I can see that the road edges are this way around the car. And also, I've seen the images over time, and I've done the tracking. And having accumulated information from all those frames, here's actually what the world looks like around you. And so pieces of software 1.0 code are being engulfed by the neural net, and it's taking on more and more responsibility in the stack. And maybe at the end of the day, this can all just be a neural net. So maybe there's a very little room for engineering. Maybe the images just come in and what comes out is just what you really want, which is the steering and the acceleration. Easily said, hard to do, but that is the final conclusion, I would say, of this kind of a transition. And there's very little software written by people. It's just a neural net that does the whole thing. Yeah, it's the holy grail, I would say.
It's a really good question here by the podcaster. How do you know it's working well? How do you establish confidence? I don't think he's talking about how do you make the public feel safe with the car driving. It's how does the Tesla team feel confident that you've got this new iteration of the software? How are you sure that it's working well? So great answer here. Great question, great answer.
How do you build confidence in the system?
Really what it comes down to is you want a very robust process for really testing the whole and subjecting it to a huge amount of evaluation, maybe both for all the individual components, making sure that, okay, the detection itself works and all the little pieces of the neural network individually by themselves, but then also end-to-end integration tests. And you just want to test the system. And you want to do this whether or not a neural net is in charge. And you want to subject it to, say, a huge amount of simulation to make sure it's working as expected. And also, of course, through driving. And so we have a large QA team that drives the car, verifies that everything is working as well as possible. So we have a number of mechanisms by which we test these systems. Another one that's big for us is shadow mode releases. So you can deploy the functionality, but it's not wired up to control. It's just making predictions, but it's not actually like acting. It's there just silently observing and making predictions. And then we sort of test it out without it actually driving the car. And so in some cases, you can also do that. So to me, this is just basically the idea that we understood the previous software is false. And fundamentally, you just need extremely good evaluation.
I really like this next set of questions and answers, and you get a feel for Karpathy's joy at watching it learn and his confidence that it is learning a lot, it is getting better, and people are really going to be amazed with how good this is.
Does ever any of the testers or you experienced something they're really surprised by and like, wow, this car is smarter than I thought?
Basically every time it drives me around in the latest full self-driving beta builds, and just the emergent properties of how it handles different situations. Like there's a bicyclist in an oncoming vehicle, and if you program it properly and the neural network works very well, you'll get these emergent behaviors where it does the right thing. So I would say like every drive, I have maybe a few of those.
I gotta imagine you still hold your hand to the steering wheel and your foot on the brake pedal just in case.
Oh, absolutely. Yeah. So the current system is the full self-driving beta build that I drive around every day. And it's actually quite capable. I think people sort of understand that the Autopilot is, it works quite well on the highway and a lot of people use it and it can keep a lane on the highway. But the latest builds that we have in the full self-driving package are quite competent, even off highway in city streets. So I was driven to get a coffee this morning and back to my house, a 20-minute drive around Palo Alto, and it was zero intervention drive. And this is a relatively routine for us. So it's not a perfect system, but it's really getting there. And I definitely keep my hands on the wheel because, it will still do not very clever things once in a while. And so there's definitely more work to be done.
There's a fun moment here where Andrej is talking about an internal joke from Tesla FSD team that has already leaked out in the past. They call Operation Vacation. This idea that at some point the software is so good at training itself that at least some of the engineers no longer need to be there and it will keep improving whether they're there or not. So that's kind of entertaining. Listen how he describes it.
Well, what is Operation Vacation?
In the process of iterating on all these predictions in the team, we are noticing that more and more of its components can be automated. So as I described the process, your neural network makes predictions. You need to source at scale mispredictions, annotate them correctly, and put them into training set and retrain the network. That's the loop. And we're noticing that you can involve engineers less and less in that loop and through a lot of automation. Now, it's not all the engineers that get to eventually go on a vacation once we've automated the whole thing. There's a large data labeling team who has to stick around, monitor the triggers, and annotate the data. But the actual software engineers who write code could, in principle, go on a vacation, having automated all the pieces of this improvement loop. So I would say it's kind of like a half-joking North Star for the team, where once these neural networks are just getting better by themselves with a lot of people in between, but just data labelers mostly, we get to all go on a vacation and the Autopilot could, in principle, just improve automatically.
Following on Operation Vacation, there's this fundamental issue that at some point it's no longer so much about the engineers who are designing the system. It's about the data labeling that's so important in making the system work. And Andrej talks here about the role of the data labelers and how they're effectively programming the system just by deciding how to label things and how important that is to them and how that's an in-house thing at Tesla rather than something that's outsourced to third parties.
Actually, as I described the system, there's plenty of design and engineering that can still go into the fundamentals. Like as an example, the system right now makes all these intermediate predictions, and there's still a lot of human written code on top of it. And this human written code is very difficult to write, and it's brittle, and it will not fundamentally, I think, scale to where we need it to be if you really want 99.99% of accuracy and comfort. There's some challenges that sort of remain, I would say, on the modeling front. And so we'll be busy with those. But if you're just talking about the perception system itself, I think its improvement can be just improved autonomously just on the raw detection itself. But yeah, as you mentioned, data annotation is not something you would do as a deep learning engineer. We spend a lot of time on it. I actually have an entire data labeling org that we've grown inside Tesla because this is so fundamental to what we do. A typical approach would be that you outsource it to third parties. We don't do that. We have a highly professional, highly trained workforce that curates our data sets. And we think that this is the right way to go because this is just a new software programming paradigm. Again, these are our new programmers in the software 2.0. And so they have to, when they're annotating examples, they're telling the system how to interpret the scene, and they are quite literally programming the autopilot. So we invest quite a bit into the org, and we keep it close, and they collaborate with the engineers very closely.
When you follow full self-driving and machine learning, there's this topic that I hear a lot, and I think you'll hear a lot, called self-supervised learning. The direct question from the podcaster about this, Andrej gives a great answer. Listen to this.
I'm curious about your thoughts on the role of self-supervised learning. Maybe you can first define for our listeners, what is self-supervised learning?
How do you train on a large collection of examples that did not have to go through a human annotation effort? Maybe people didn't go in and they didn't put bounding boxes around fire hydrants. Maybe it's just a huge amount of data and fire hydrants are featured in some of it. And maybe there are other objectives than explicit matching of human annotation that we can use to pre-train these networks so that they develop these representations. So there's many ways that people are trying to arrange it. As one example of many that seems to work relatively well is, for example, you could try to predict the future. And so it's not that we don't use labeled data. It's that we are using data that is annotated for free. Because when you have a video of what happened in the world, you sort of have the future and came for free in the data stream. So you're still training the network to predict a thing, just like normal supervised learning, but you happen to have that thing for free without human effort. And so self-supervised learning is a class of approaches that try to leverage the structure of the data and try to take advantage of the free supervision that we have just in the raw data streams, instead of to sort of get the networks to arrange themselves into configurations that kind of understand the world so that it's much more efficient per label to train anything else. Fire hydrants might not be like the best example, but yeah, as an example to predict the future, you have to actually understand the layout of the entire scene and how people and cars move and interact. And so this prediction problem forces the neural network to understand that, hey, there are cars, they move around. There are people, they move around. They avoid these areas. And so when I need to predict the future, I need to actually parse the scene to do that properly. Yeah, there is a class of approaches, and we have tried a number of them. I do find that in these incredibly valuable applications, just paying for the labels is often the right way to go instead of paying researchers. But I think I basically kind of agree with that. Yeah, this is, it's not ideal. And there are some techniques that, as you mentioned, are seeing quite a lot of traction. And we have experimented with a number of them internally at Tesla.
There's actually a pretty interesting contrast within the self-driving industry between this idea of just labeling everything and helping the software learn versus totally self-supervised learning. Comma.ai is run by George Hotz, or George Hotz, I don't know how to pronounce it. He's been interviewed on Lex Friedman's podcast as well. And Hotz seems to embrace the idea of just pure self-supervised learning, not doing any data labeling at all. And here Karpathy says, yeah, we've tried that. He feels that the data labeling approach is more efficient, that it's better to spend money on data labeling to get the job done than to just rely on researchers figuring out how to get self-supervised learning to work so that the car can learn to drive on its own. That's his impression of it. Hotz has a different impression of it. My hunch is Tesla's going to win this race by a long stretch because it has more data, it has more compute, it has a lot of things going for it. In the long run, it very well may that Comma.ai comes in second because their approach is still a pretty good approach and nobody else is doing anything close. Another bit here coming up, it's kind of interesting that boring data is bad. So Karpathy explains that you want to feed the software interesting data, data that it needs to learn from. If you feed it boring data, you're diluting the value of your data set. You want to give it the hard stuff so it can learn from the hard stuff. If all you give it is driving down the highway, following lane lines, then that's not much to learn from, and that can offset the value that you're trying to get into back propagating through the neurons. Listen.
And once you go self-supervised, you can use infinite data effectively. So all data works, right?
You have to be careful though, because more data is not always better. If you add boring data into your data set, you may actually be diluting your data set, right? Because your neural network will train for, like I mentioned, 3 weeks, and it's going to see some number of examples in its training. And if a lot of the examples are boring, it's not going to learn a lot. So you actually want to be very careful with and this is why I talk about curation of data sets. It's an active process of adding hard examples and subtracting the easy examples often. And a very easy way to see this is, of course, if I had just a single image in my massive data set, of course, that's not helpful. So you really want to pad out the variability. And that's why I use active terms like curation when I talk about data sets. It's an active process to curate the data set.
Next up, a really fun bit about Tesla and chips that it uses for FSD, and maybe a hint about chips for Dojo.
Building their own chips for AI compute. Why does that matter?
So there's many possible answers to that, of course. I think to a large extent, Elon sees AI as just a fundamental pillar of a lot of this technology and wants to invest into internal teams that develop a lot of this technology and co-design everything. Tesla is definitely about vertical integration and squeezing out a lot of juice from the benefits of that. To a very large extent, of course, we own the entire manufacturing of the vehicle in the factory. And then we own a lot of the pieces of, the hardware itself, how's it pointed, all the design decisions. And we own the cluster, we own the data labeling team, and also we own the inference hardware, the chip that actually runs the neural network on the car. To us, it's just another opportunity to co-design everything, specifically for the purposes of self-driving. And so the chip is designed with the kinds of neural networks we want to run in mind. And the hardware itself is just targeted to the operations that we want to run and do that very efficiently. So really, it's a theme of Tesla, and it allows us to co-design all the components to work together towards a single goal. In this case, full self-driving. This hardware for deep learning actually kind of has two broad areas now. There's hardware you would use to train neural networks, and that looks very different from the hardware you might want to use to run a neural network. So running a neural network is computationally much more straightforward thing. The neurons just have to fire in a sequence. If you're training a neural network, there's a lot more that goes on there because you have to run the neural network forward, but then you also have to implement the backpropagation algorithm, and you have to run the backward pass, and you have to update the weights. And there's a lot of technical details as to at what precision do you run all this mathematical precision in terms of the numbers involved. And so there's a lot of details that make the training a much more heavy endeavor and the testing, the inference, a much simpler endeavor. And so, as you mentioned, we currently have a chip for inference that we own and we've designed and is in all the cars. And we are also working on a training computer. And this is Project Dojo. And Elon has sort of alluded to it on a high level a number of times. And it is really just pushing this co-design even further. And we have a rough understanding of what these computational workflows look like for training neural networks for the Autopilot. It's a massive amount of video training. We are building a chip directly sort of designed for that kind of a computational workload. And so, that's absolutely an active project currently at Tesla.
So Dojo is coming. It's not just Elon. Andrej Karpathy talks about it too. Sounds to me like Dojo is not quite there yet. They're still designing the chip. I'm not sure what that means. I thought we were heading towards Dojo going live in the third quarter of 2021, maybe fourth quarter 2021, and that's really going to accelerate the learning. Not really clear what Karpathy meant when he said we're still designing it. It sounds like they're really close, but it sounds like they're not ready to start having a factory start spitting out chips. It was unclear how long that's going to take, and I remember somewhere Elon talked about managing the heat from these chips. So Who knows when Dojo is going to come out? I think when Elon said third quarter, that might have been Elon time. And with Karpathy talking this way, maybe Dojo is going to take just a little bit longer. I'm hoping Elon's right and it's happening sooner. I think the point about Dojo, the training computer, being co-designed with the inference computer, with the computer in the car, this is going to enable faster training. Remember, he talked earlier about the training taking 2 or 3 weeks. I think Tesla's probably already training quicker, like 1 to 2 weeks, maybe even 1 week. But I think one of the goals with Dojo is if you can train in a day or a day or two, then you can increase the rate of iteration. That's one of the things that Tesla has been very good at. Elon's companies are very good at is rapid iterative engineering. You can iterate and do another one and do another one and just keep getting better. Number one, if you can improve faster, if you can improve more with each iteration, that's good. If you can do the iterations faster, that's also really important. So if each iteration improves by twice as much and you iterate 5 times as often, then you're improving 10 times as fast. Now Karpathy dives a bit into the larger problem of AI and specifically regarding human language with GPT-3 and the need for more compute, that the real limitation on a lot of things that they're trying to achieve in AI generally has to do with having more computing power. And after that, we're going to talk a little bit more about this. He's going to dive back into Tesla and how this relates to Tesla.
More compute is one of the fundamental limiting blocks right now for a lot of things, for a lot of domains. OpenAI is right now focused on, for example, natural language processing, for example, with their most recent work on GPT. So what they're doing there is it's a language modeling task where the neural network is generating language, text. And so you can feed it text and it will continue text, or you can ask it to produce text with certain properties, or it will answer your questions, or it will talk to you. So what's happening there is the algorithms, again, in this setting are actually quite well known and understood. As you mentioned, the neural network takes the form of this transformer. You're training it in a very kind of standard regime with backpropagation, stochastic gradient, and so on. So that's understood. So the algorithms are not the bottleneck for them. The data set is also not a bottleneck for that class of problems because we have the internet with huge amount of text. So in that regime, also, you are not upper bounded by data sets, but you are upper bounded by the compute available to you, which really restricts the size of the model that you can actually use. And like I said, in deep learning, we are blessed with algorithms that seem to continue to work better and better as you just make them bigger. You're literally just adding neurons into the system and it works better. And so OpenAI is primarily gated by compute in this setting. If they could train a bigger network, it would work better. And that's not the way it used to be in AI. We used to be bottlenecked by algorithms. And so what a beautiful place to be. If they could just run a bigger network, it would work much better and the results would be even more magical.
And is that true for Tesla also?
Yes, I would say so. And neural networks have this property in general that, yeah, if you make them bigger, they will almost always work better. And, in the limit, you can, for example, use, this is slightly more technical, but you could use model ensembles, you could use dropout, and a lot of techniques to basically make sure that these models work better when you scale them up. And so we are also limited by compute to a large extent, and we have to be very creative in how we squeeze out all the juice from all the flops that we have available on the car. And so that's the case also on the car, but also during training for us, right? So you want to train as big of a network as possible. And for us also, you have to consider the data set and to whatever extent that is a bottleneck, and the algorithms and the models and to whatever extent that is a bottleneck. And so for us, for example, we do a lot of manual labeling. We are also looking into ways that you can train on data without having to label with a human. You can use sensors, expensive sensors, to annotate your data. Maybe you have a few cars to drive around with, say radars or LiDARs or any other sensing suite you want that gives you extra information about the scene. And that can function as annotation for computer vision. And so computer vision can be matching those sensors and imitating them. And so you have sensor annotation, human annotation, or self-annotation, like predicting the future.
Next up, Karpathy compares Tesla's efforts with full self-driving to other efforts, particularly Waymo, although I don't remember if he names Waymo in it, but it's pretty clear Waymo is one of the targets of what he's talking about.
How do you see the Tesla effort different from the other efforts?
It's a very good question because it is very different and it is not obvious. So, for example, there was a video just recently released where someone used a Waymo car and the Waymo drove them to some location. I forget the details. And then they used the Tesla Autopilot full self-driving beta build, and it also drove them there with zero interventions. And so both cars took the same route and got to the same spot with zero interventions. And so to a third-party observer just looking at this, these are cars, they take right turns, left turns, they navigate you to where you need to be. It looks the same. But under the hood, the systems are actually extremely different, like quite different. So the approach of Waymo and many others in the industry, and I would say in the industry, we'll see this two classes of approaches, really. And one is Waymo-like, and the other is Tesla-like, I guess in my naive sort of like description of it, I suppose. And in the Waymo-like approach, you are going to first outfit the car with many more sensors, in particular, the use of quite expensive LiDAR sensors that are on top. They give you range sensing around you. And you also have these high definition maps. So you need to drive around before you make the trip, and you need to pre-map the environment in very high definition. And then when you are driving, you know exactly where you are on that map. So you know exactly how to stay on it and how to drive. And this is very different from what the Tesla car is doing, because first of all, we do not have very expensive sensing. We just have a few cameras that give us surround view. And by the way, that's already a lot of information because each camera is, say, several megapixels. And so you're getting many millions of observations of what's around the car when each ray really is of brightness is telling you something about the world. So you're getting a huge amount of information from cameras that is very, very cheap and economical to produce. And we do not use high definition maps. So we have very low definition maps that are kind of like a Google map. So it's telling you that, hey, you should take a right turn, left turn, etc. But we do not know to a centimeter level accuracy where the curve is. Everything is coming from the system at that time through vision. And so the car is encountering these intersections and these areas for the first time, basically, as it's driving around. And it needs to look at the images and needs to decide, these are curbs, these are lane markings, this is how many lanes there are, this is where I should be to take a left turn. And so it's a much higher bar, much harder to design, but it's also much cheaper because the sensor suite is just cameras. And it's not specific to a location that you had to pre-map. So our system is very cheap and it will work anywhere. What this allows you to do then is that this affords you scale. So Waymo can have maybe a few hundred cars or something like that. We have millions of cars. And as I mentioned, scale is incredibly important to getting AI to work because everything is about data set curation. And so I do not see how you can fundamentally really get a system to work well in absence of scale. And so I think I would much rather give up some sensing in return for scale in AI problems.
Just one other quick detail that I think Karpathy left out is in addition to the lower cost of Tesla's sensor regime, where Tesla basically has 8 cameras and some other low impact sensors, and Waymo has this big LiDAR and a lot more sensors, Waymo's approach uses a lot more energy. Tesla's approach minimizes energy consumption. And if you minimize energy consumption, you have a lot less impact on the range of the vehicle. So that's a really, really important detail. When you slap that LiDAR thing on the roof, it uses a lot of juice. It also creates a problem with aerodynamics because that thing is not aerodynamic. You're going to greatly increase your drag coefficient, and it's going to mean it's harder to push through the air, and that's going to shorten your range as well. And this matters when you're dealing with EVs. In the last bit of this interview, you're going to hear Karpathy talk about the future, how optimistic he is, how much change we've seen in artificial intelligence over the last decade or so, and how rapid he sees change coming in the future, and how good that's going to be for us.
And I'll get to live, hopefully, 4 more decades or something like that, maybe. Like from 2012 to now, been a complete transformation of AI. And a lot happened in a decade. And so if I'm going to witness something on those orders of magnitude in the next 4 years, it's really mind-boggling to extrapolate. And fundamentally, we have these algorithms that seem to be only upper bounded by the data and the compute. We're going to get more compute, and we are specializing all of our hardware to neural networks, and all of that is ongoing. Our current processors actually are not very specialized for running neural nets, and there's a lot of low-hanging fruit there. And also the size of the field has grown, and so there's a lot more brain power going into improving everything. So there's this exponential return on all of this investment in hardware and software. And so you shouldn't expect linear improvements. You should actually expect some kind of an exponential improvements. So it gets even more mind-boggling. So I think in the short term, we're absolutely going to see much more automation, be it self-driving cars, drones, or warehouses. And that's very easy to predict. But I think on the long term, that's where it starts to get kind of even more dicey, because I joined OpenAI. OpenAI is basically a AGI project, artificial general intelligence. So the idea is we're trying to develop fundamentally a artificial brain that thinks and wants and acts and functions like a human being. So I would say next to a visual cortex, we sort of have a check mark, like that part of the brain. We sort of maybe like understand the principles of, but we certainly haven't understood the entire brain and how, decision making is done and so on. But I think we are, with robotics and so on, we are probably going to make a massive dent into that next decade or 2 or 3. Yeah, I think we're probably going to see some very exciting things come from AI, because the technology is not really upper bounded in any like real way. And it's mildly concerning, but kind of exciting. So I think we'll see what happens.
Mildly concerning, but exciting. I'd like to say that's what my wife thought of me on our first date, but it was probably just mildly concerning and not exciting. Anyway, I hope you liked this video. I hope you learned a lot. I think Neuralink is actually going to play in with AI. We're going to see a lot of intersections in that. There's a lot of great stuff coming. In terms of emulating the human brain, I think we're going to see artificial intelligence and machine learning interact with Neuralink in understanding how the human brain works. And that's going to go even further towards helping create artificial general intelligence, which is going to be a really fun ride. Or it'll kill us. We'll find out. If you like this video, please check out my other videos. Please support this channel on Patreon, links below. T-shirts, Elon Be Less Wrong, and other t-shirts, links below, elonbits.com. Check out the book, Fair DUI. Great book if you drive. Not if you don't, but if you do drive. And thank you so much for watching.